I went ahead and opened up everything else up on the pie chart since we're on our last packet here. Chapter 5 starts off with systems of equations where you've got more than one equation with more than one variable. And the first one's just checking to see is the ordered pair a solution or not. If it is going to be a solution, you have to get a yes in both equations. So we're just going to plug our numbers in and check it out. So if I do the 1, 4, in my first equation, does 4 equal 8 times 1 minus 4? Yes, it does, right? So then I would check it in my second equation. Negative 3 times 1 plus 2 times 4, does that equal 5? Yes, it does. So we get a yes and a yes. So this point works in the system of equations. It works in both of my equations. So then we do the next point, negative 7, negative 8. Testing that in my first equation, the y value is negative 8. Does that equal 8 times the x value of negative 7 minus 4? Nowhere near negative 8. Now there's really no reason to check it in the second equation because unless you get a yes and a yes, the answer is no. So unless you want to spend extra time plugging numbers in, if you get a no, you can just right away go ahead and say, oh, that one's no. Doesn't work in both. The next one, negative 3, 5. So checking that in my first equation. 5 equals 8 times negative 3 minus 4. Does that one work? Nope. So again, we don't even have to bother with the second equation. And then the last one, negative 4. So negative 4, does that equal 8 times 0 minus 4? That's a yes. So since we got a yes in the first, we better check the second one. Negative 3 times 0 plus 2 times negative 4, does that equal 5? No. So since we got a no, it's still a no. So the only way to have a yes is to have both of them be yeses. So the second one we are going to check, putting in our 6, 0. 0 in for y, does that equal negative 2 times our x value of 6 plus 9?
What's your sign between 0 and 2?
Negative 2 times 6. That is a sloppy equals and then the negative kind of blended in. Putting it in here. Does 0 equal negative 2 times 6 plus 9? No. That's a no. We can mark no. And we're going to check for 1. So y is 1. Does 1 equal negative 2 times 4 plus 9? Yep, that's a yes. So since that's a yes, we better check the next one. 4 times x is 4 plus 2 times y is 1. Do we get 18? Yep. So we got a yes and a yes. We can mark yes. We should switch colors. They're blending into each other. 5, negative 3. Checking that in my first equation. Y is negative 3. Does that equal negative 2 times x, which is 5, plus 9? No, right? Negative 10 plus 9 is only negative 1, not negative 3. And the fourth point, we have negative 5, 19. So So y is 19. Does 19 equal negative 2 times negative 5 plus 9? Yep. Since that's a yes, we better try it in the second equation. So 4 times the x value of negative 5 plus 2 times the y value of 19. Do we get 18? Two times 19 is 38, right? 4 times negative 5 is minus 20. Whoops, plus. What's a negative 20 plus 38? 18. Looks to me like it works. We get a yes and a, oh, I forgot to mark the no up here. That was the third one was no. The fourth one looks like it should be yes. As you're napping on me. All right, so 0, negative 7. Putting that into my first equation. 2 times 0 minus 5 times negative 7. Do we get an answer of 4? No. Negative 8, negative 4. So 2 times negative 8 minus 5 times negative 4. Do we get an answer of 4? Yes, we do. So we got to check it in our second line. Our second line says negative 3 times our x value of negative 8 plus 2 times our y value of negative 4. Do we get an answer of 5? What did you say?
No.
Nope. 24 minus 8 is not going to be 5, right? So we got to know. Almost lost it. Negative 3, negative 2. So 2 times the negative 3 minus 5 times the negative 2. Do we get an answer of 4? Negative 6 plus 10. Yes, right? Putting that into my second equation. Negative 3 times the x value of negative 3 plus 2 times the y value of negative 2. Do we get 5? Yes, we do. So we got a yes and a yes. Means we get a yes. And the last point, 1, 4. So 2 times the x value of 1 minus 5 times the y value of 4. Do we get an answer of 4? No, we don't. Since that's a no, we can just mark no, and we're done. So just plugging the numbers in, checking to see does it work or not. If they're both yeses, we can mark yes. The next ones, we're classifying a system of linear equation from its graph, and actually each one of these is going to have 3 parts, one of each kind. If I am drawing a system of equations that has 2 lines, there are 3 ways I could draw it. The most common way is I have one line through my graph, I have another line through my graph, and because I had 2 pens in my hand, it still wrote green. And my 2 lines cross in a point, and that point where they intersect would be a point that would say yes and yes when I plugged them in. This is called consistent because it does have an answer. Make sure I spell it right. Independent. Independent means 1. So you get one unique solution if you have something that looks sort of like that. The next probably most common way of drawing two lines is when you have two lines that, if I could draw, were parallel to each other. If those two lines are parallel, they're never going to touch each other, so they're never going to have a solution that's common to both of them. Those are called inconsistent and will have no solution. And the third way to draw two lines. If I can draw straight, which you can't, is when I have one line right on top of the other line. This is called consistent dependent and has an infinite number of solutions because every single point on the line works in both lines because they're really the exact same line. One line's right on top of the other line. So all they're going to have you do on these ones is pick out which kind it is, how many solutions it has, and if there is a solution, what is a solution. So, first one on number 4, we've got the two parallel lines. If the two lines are parallel, they're not going to intersect, so we have inconsistent with no solution. And then I've got to keep track of where I'm at. The second one on number 4 intersects in a point. If it intersects in a point, it's called consistent independent. And then I'm going to have a unique solution, and my unique solution is going to be the point where they cross. So it's going to be at 1, 3. 1, 3 would be the point that would work if I substituted in both of those equations up there. So if I was really bored and I wanted to check, I can put the 1 and the 3 in and see that it works in both of my equations. The third one on number 4 is the one where they say line 1 is equal to y equals negative 3x minus 3. Line 2 is 3x plus y equals negative 3. But if you rearranged it and solved it for y, you can see it's the same line. I've got line 1 right on top of line 2. Those ones are consistent dependent and will have infinite many solutions because every point on line 1 works on line 2. So, number 5. That first one is what? Consistent independent. And what does it have for solutions?
0, 4.
It has a unique solution at 0, 3. Right? If I count up, there should be at 0, 3. The second one on number 5. I've got those two lines that are parallel, so those are inconsistent and have no solution because they never touch each other. If my board would just stay where it's supposed to be. So the third one on number 5, one line right on top of the other line would be consistent dependent and have infinitely many solutions because every point on line 1 works on line 2. And hey, it didn't move all the way on me. Number 6. The first one would be consistent independent, and it would have a unique solution at 3, negative 1. Darn, it moved on me again. And the next one is consistent dependent with infinite many solutions, right? And the last one on number 6 is inconsistent and has no solution since my lines are parallel. So there are a ton of ways to solve systems of equations. One of the ways is by graphing. I can graph my two lines and then check to see if I have them intersecting, if they're parallel, or if they're the same line. So this one's in standard form. Easiest way to graph them when they're in standard form, just finding my x and my y intercept, right? If I put 0 in for y, my x-intercept is at put 0 in for y, my x-intercept is at -2. Because I'm just dividing this number by that number, right? So my x-intercept is -2. My y-intercept, if I put 0 in for x, my y-intercept is going to be at -6. 3 times 0 plus y equals -6, so that gets rid of that, and I just get the -6. So there's my first line. I'll try to draw it straight on Alex. I'll make you draw it straight. Use your ruler. The next one is in slope-intercept form. The easiest way to graph that is probably just by using the y-intercept and the slope. My y-intercept is at 1. My slope is 1/2. So from that point, I'm going to go up 1 over 2, up 1 over 2. And if I draw my line straight, those two things do intersect in a point. So what is the solution to this system of equations? -2, 0. And if I didn't draw very straight and I needed to check, I could plug them in and check, but Alex will make you draw straight, so you don't have to worry about having a crooked line like I have. Number 8. Then we have x plus 2y equals -6. So if we find our x-intercept, putting 0 in for the y, x equals -6. And if I find my y-intercept, putting 0 in for x, y is going to equal -3. -6 over 2 is -3. So again, try to draw your lines straight. Mine's not very good. Second part, y equals -1/2 x plus 1. So my y-intercept is at 1. My slope is -1/2, so I'm going to go down 1 and over 2, right? And so the solution to that system of equations will be no solution, because they're not going to intersect, so you're going to pick no solution. And number 9. -x plus 2y equals 6. They must like 6 that day. I was bringing problems up. Finding my x-intercept, if I put 0 in for y, x is going to equal -6. 6 divided by -1 is -6. And if I put 0 in for x, I'm going to have 3. 6 divided by 2 is 3. So I can then connect my dots and draw my line if I could draw anywhere near straight. The second one, my y-intercept is at 3. My slope is up 1 and over 2. And so if I connect my dots, I can see that my solution would be infinite many solutions, since one line's right on top of the other line. Another way of solving a system of equations is by the substitution method. If one of my equations is solved for a variable or is easily solved for a variable, substitution is a good method. In this case, the y is equal to 3x minus 4. So we're going to take the 3x minus 4, substitute it in for the y on our second equation. So in our second equation, we have 4x plus 3, and we're going to replace the y with the 3x minus 4 equals my 27. Now I have an equation that just has one variable that I should be able to solve. So 4x plus, using my distributive property, 9x minus 12 equals 27. 4x plus 9x would give me 13x minus 12 equals 27. Adding my 12 to move it over, 13x equals 39, and dividing, x ends up being equal to 3. Once I find x, I still need to find y, so I can use that top equation that said y equaled 3x minus 4 and replace the x with my 3 that I found. So 3 times 3 is 9. 9 minus 4 gives me 5. If I wanted to double check and make sure that was right, I would check it in my second equation. I'd say is 4 times 3 plus 3 times 5 equal to 27. 12 plus 15 is 27. Yep, checks out. So I know those are the right answers. So number 11. This time my second equation is set equal to x, or x is set equal to 3y minus 18. So this time we're going to replace the x in the first equation with the 3y minus 18. So what would we have for our new equation? So multiplying that out, we would get combining my like terms, adding my 90, and dividing. It's 95 divided by 19. With 9? 5? Can't hear you. 5, okay. By the way, I'm Alex. These will all come out to nice whole number answers, so you won't have to worry about having some weird fraction answer like you might in a textbook. So if you are getting a weird fraction answer, go back and check your work. I knew y was equal to 5. I still need to find x. So I know that x equals 3y minus 18. If I put 5 in for my y, x then is going to equal negative 3. 15 minus 18 is negative 3. Sometimes you have both of your equations in standard form, but you'll have a variable with the x or the y that doesn't have a coefficient other than 1. The leading coefficient is 1, so it's easy to solve it for x or y, and therefore substitution works. I still probably use the elimination method, but substitution works. So what I need to do is I need to set this one equal to y by moving my 3x to the other side. So that's going to become a positive 3x minus 5. And if you put negative 5 plus 3x, still going to work out okay. But look for one that doesn't have a coefficient other than 1 in front of it and solve it for that so you don't have any weird fractions. Substituting in for y then, my new equation would be equals 12. Okay, multiplying 2x minus 15x plus 25 going to equal 12, right? 2x minus 15x would give me negative 13x plus 25 equals 12. I'm going to minus my 25, so negative 13x equals negative 13. So x is going to equal 1, right? I figure you guys know how to solve. So x is equal to 1. I still need to find my y value. Over here we solved for y. We said y was equal to 3x minus 5. So if x is 1, y is going to be negative 2. And again, if I just quickly check it, 2 times 1 is 2, negative 5 times negative 2 is 10, 2 plus 10 is 12. Yep, it checks out, so I know I did it right. The next one says solving a system of linear equations using elimination with multiplication and addition. Some books will call it the elimination method, some books call it the addition method. In any case, usually you use this method when you have both equations in standard form so that the x and the y are both on the same side. And your goal is to make opposites either in front of the x's or in front of the y's, doesn't matter which one, so that you can cancel out one of your variables. So just because my coefficients in front of my x's are smaller, I'm going to get rid of my x's. I want to find the least common multiple of 3 and 4, which is 12. So I want to make one a positive 12 and one a negative 12. Since my signs are already opposite, I don't have to worry about changing the signs. So basically I'm just multiplying by the opposite number. 3 there and a 4 there, both of them being positive so that my signs don't change when I multiply. 3 times negative 4x would be negative 12x. 3 times a positive 9y is a plus 27y. 3 times 19 must be somewhere around 57. On the bottom, 4 times 3x is 12x. 4 times negative 4y is negative 16y. 4 times negative 17 is negative 68. I now have opposites in front of my x's so that when I add, I eliminate my x's from the equation. 27 minus 16 gives me 11y. 57 minus 68 is negative 11. So when I divide, I get my answer, y equals negative 1. Found one of my answers, I still have to find the other one. You can use either equation, it doesn't matter which one. Normally Alex will just use the top equation, but you can use the bottom one if you want to. I'm going to use the top one. So negative 4x plus 9 times the y value, which we're going to replace with the negative 1, equals 19. So negative 4x minus 9 equals 19. If I add my 9, negative 4x equals 28, and when I divide, x equals negative 7. Same thing on our other system of equations. If I really want to check my answer, I can substitute it into the opposite equation that I used here. So 3 times negative 7 would be negative 21. Negative 4 times negative 1 is a positive 4. Negative 21 plus 4, sure enough, is negative 17. So I know I did it correctly. So number 14. Would it be easier to get rid of the x's or the y's? I think it'd be easier to get rid of the y's. Why do I think that the y's would be easier? Because 3 divides into 6 evenly, and then I only have to multiply one equation times something instead of both of them. Not that it wouldn't work to do the x's, but it's less work if I just take the top equation times negative 2, because then I already have an opposite of negative 6 in front of my y, and then I have less work to do. So negative 8x minus 6y equals negative 2. The bottom equation I'm just going to leave alone. 7x plus 6y equals 7. Otherwise, if I was going to get rid of the x's, I'd have to take the top equation times 7. The bottom equation, I'd want my sign to be negative, so I'd use a negative 4. So I had 28 and negative 28. Solving. I'm going to get negative 1x equals 5. So x equals negative 5. Plugging that into my top equation, 4 times my x value of negative 5 plus 3 times my y value, which I don't know, equals 1. So negative 20 plus 3y equals 1. I'm going to add my 20 when I move it over. So 3y equals 21, and if I divide, y ends up being equal to 7. Number 15. That one doesn't look like either the x's or the y's would be much different. You want to get rid of the x's or the y's? X's, okay, so we're going to take our top equation times 5 and our bottom equation times 4. Again, these already have opposite signs, so both of those will be positive on the outside. So negative 20x plus 35y equals 20. On the bottom, positive 20x minus 24y equals negative 20. Well, that makes that one easy. So I get 11y equals 0, and 0 divided by anything, still going to be 0, right? Y equals 0. Plugging that in, negative 4x plus 7 times 0 equals 4. So negative 4x equals 4. So x equals negative 1. (16, 17, and 18). Most of these they'll probably have you solve by the elimination method. Sometimes substitution works okay also. But to get across, we really could have 3 different kinds of solutions. Could be no solution because the lines are parallel. Could have a unique solution like all the other ones we just got done doing. Or it might have an infinite number of solutions. So in order to get no solution, the variables have to cancel out and you have to get something like 0 equals 5. In order to get the infinite number of solutions, that's the one where the variables canceled out and get 0 equals 0. All real numbers are solutions. So if I'm going to solve this first one, I already have opposites, so I can just add. This will be 0, this will also be 0, and I get 0 equals 10. 0 doesn't equal 10. That tells me that if I would graph those, I would have parallel lines, and I get no solution there. If I solve the next one, I get 0 plus 0 equals 0. So 0 equals 0. That tells me that this system is going to have infinite many solutions, and although the bottom of that is cut off, when you have that for a solution, they're going to make you rearrange one of the equations, which should be the same equation, and solve it in terms of y. So if I have x plus 3y equals 3 and I want to solve that for y, put it in slope-intercept form. 3y is going to equal negative x plus 3. I then divide by my 3, and so y is going to equal negative 1/3 x plus 1. And so that will go down there in that answer. See if I can get the whole thing on there. There we go. So number 17, if you add those first thing I need to do on that equation is I don't have that second equation in standard form. So I probably want to move the 2 over, right? Plus 2. Now if I add those two equations together, I'm going to get 0 equals 0. So my solution is that I have infinite many solutions. And if I solve that top equation for y, that one's pretty easy to solve for y, I would get positive 2x minus 2, right? Because I just need to move my 2x to the other side, so it becomes positive. The next one, I see that I do have opposites in front of my y's, so I can just go ahead and add those together. If I add those together, I'm going to get not 0, negative 12. Negative 4x equals negative 12. So this one is one that's going to solve and have a solution, because obviously I can solve this for x. X is going to be equal to 3, right? So now I've got to find y. Do we want to put x in the first equation or the second one? Doesn't matter. I'm going to use the second one just because it has a plus y. So negative 2 times 3 plus y equals negative 6. So negative 6 plus y equals negative 6. And if I solve that, I get 0. So this one does have a unique solution. The solution would be the point 3, 0. And the last one on this page, stay where I want you to stay. Keeps wanting to go farther down. So, again, we don't quite have that first one in standard form. We probably want to rearrange that. So I'm going to have negative x plus 3y equals 6. And when I add those together, I'm going to get 0 equals 0. So our system has infinite many solutions, which means I have to solve one of those equations for y. Negative 3y would equal, that's going to be a negative x minus 6 then. And if I divide by negative 3, then y is going to equal 1/3 x plus 2, right? And the last one on here, if I add those two together, I get 0 equals negative 18. So we know that the system has no solution. All right, so that should be the beginning of chapter 5 stuff.